All right, to be able to analyze any sort of physics problem in 2 or 3 dimensions, we need to develop some vector math. So as we've already learned, in nature there are quantities that are scalars and there are quantities that are vectors. Scalars are things like temperature and mass. They have a magnitude. The temperature is 80 degrees, and there's units, degrees Fahrenheit. And vectors are quantities with a magnitude, a direction, and units. That could be something like velocity. You are driving 20 meters per second east. Now there are 3 ways to represent a vector mathematically. The first way that we'll be talking about in this video is called a graphical representation. That just means you draw a picture. You draw it as an arrow. The other 2 representations that we'll be discussing in the next video are the magnitude angle representation and the component representation. You can do math with vectors in all 3 representations, although it's easiest to do math with vectors in component form. So that one's really going to be the key to all of this. But for now, in this video, we'll take a look at vectors in graphical form, learn some of the basic properties of vectors, do some simple math with them, and then the next video we'll get into some more detailed calculations with these other 2 representations. Okay, so a graphical representation means you're drawing a picture of the vector as an arrow. So you might start out with a coordinate axis, and maybe my vector again is a velocity. Maybe it's 65 miles per hour east. You're driving on the 101 freeway from Woodland Hills to Encino. So what you need to do to represent that vector graphically is draw an arrow where the length represents the magnitude and the direction represents the direction. So if I'm driving 65 miles per hour east, my vector might look like this. Or it might look like this. Or it might look like this. Now, notice something. I didn't draw these on the same place on this graph. When you draw a vector in graphical form, it doesn't matter where you draw it. The only thing that matters is that you get the length right and the direction right. The placement on the picture is irrelevant. So in fact, all 3 of these vectors are equal to one another. They all represent the same velocity because they all have the same length, or I tried to draw them with the same length, and they all point in the same direction. They all point to the right, or east. So vectors are equal. If they have the same length and point in the same direction. Or, in other words, if they have the same magnitude with units and direction. As another example, maybe I have some vectors that look like that. All three of those vectors are equal to one another. They all have the same length and they all point the same way. If I drew a vector like this, that vector is not equal to the other three. It has the same length, but it points in the opposite direction. Similarly, if I had a vector like this, same length, but a completely different direction. So neither of those is equal to the other three. All right, I'm just going to erase this side of the board as I go through the different properties. Okay, the next thing we might want to do with vectors is add them. So yes, you're learning addition today in this lecture. But adding vectors is not as simple as adding regular numbers or scalars, because imagine that you have a velocity that's 65 miles per hour east, and you have another velocity that's 45 miles per hour southwest, and you want to add those together. Well, somehow you have to take into account all those directions. And it's not just as simple as adding the scalar part together. So let me draw you a picture. We'll do graphical addition, and then when we learn about component form, we'll do this with numbers. So let's say that we've got two vectors and they look like, how about vector A looks like this, and vector B looks like this. We want to add A plus B. So how do we do that? Here's the process. Remember I said it doesn't matter where on your picture you place a vector. So we can move these around as we like to make things more convenient for doing this process of addition. So I'm going to take my vector A and move it so it starts at the origin. This will be easier for me to visualize. So vector A, I'll keep it the same length and the same angle as best I can. I'm drawing this freehand. So there's vector A. And now, at the end of vector A, I'm going to place the beginning of vector B. So let's take vector B and move it, because we can move these however we like. We'll move it to the end of vector A, keeping that same length and direction. Now the sum, A plus B, is the vector that connects from the start of A to the end of B. So let's call that vector C. Vector C connects the beginning of A to the end of B when you place A and B head to tail next to each other. Let me show you another example so you can see how this process works. How about vectors C and D, where vector C maybe looks like this, And vector D looks like that. So here's how we do it. We take vector C and we place it at the origin of a coordinate system, keeping its angle and magnitude the same. So there's vector C. And now we take vector D and place the start of D at the end of C. So D goes here. And we connect the beginning of C to the end of D. And there's our resultant, vector E. All right, next thing we need to do, we need to learn how to take the negative of a vector. The negative of a vector is super easy. You flip the vector 180 degrees, keeping the length the same. So if this is A, then negative A would look like that. If that's B, then here's negative B. Just flip them 180 degrees. And now that we've defined negatives, that means we can define subtraction, because subtraction is just adding the negative. So A minus B is the same thing as A plus negative B. So let's do that for our A and B vectors there. Take vector A, place it at the origin, and then we take vector negative B and connect it to the beginning of vector A, and our resultant looks something like that. There's our A minus B vector. And again, I'm drawing this by hand, which is pretty imprecise. Things will get numerically precise once we learn how to do this. Don't worry when you're looking at examples and practicing with these that it's hard to draw. This is just so you can get a picture of what it looks like, but this is not the precise way to do it. All right, there's one more thing that you need to know how to do, and that is scalar multiplication. This is also pretty easy. This means multiplying a vector by a scalar number. For example, what is 3 times vector A, using the same vector A from up here? You might be able to guess what happens. You just make vector A 3 times as long. You keep the angle the same, but make the length 3 times the original length. So 3 times A, if we started from the origin, would look something like that. And maybe 3 times negative B, we can start this wherever we want. So maybe I'll start negative B here. 3 times negative B would be something like that. Now you might ask, why are we only multiplying by scalar numbers? Why can't we multiply a vector times a vector? The answer is you can, but there are several ways of doing it, and they are more complicated, and we don't need them. We might get into one method later on in this class, but for now, we don't need to use those. But those other types of vector multiplication do come up in all sorts of physics and engineering applications when you get more advanced. Okay, so that's our graphical math, or math by drawing pictures. And now in the next video, we'll do math with numbers.